Now, there are several ways to approach measurement on the quantum level. Let's begin by considering something else we may already know. So consider the concept of spin. To do so, let's take a look at a given set of particles. When measured using a certain instrument or apparatus, the particle's spins may be considered either spin up or spin down. Now, if we place two more apparatuses in the paths of these particles, one where the particles with spin up have been deflected upwards, and the second where the particles with spin down have been deflected downwards, we will find that those deflected upwards in the first measurement will still have been deflected upwards in the same direction during the second measurement. The same goes for those with spin down. Long story short, if we measured an electron with spin in some direction, say angle 0 degrees, when we repeat the same measurement, we will still receive the same results. That, however, raises another question. Our apparatus here only measures spin in two directions, up at 0 degrees and down at 180 degrees. However, when we take measurements in different directions, something curious occurs. Let's again send the same sample of electrons through the first apparatus, then place two more apparatuses in their appropriate places, this time rotated by 90 degrees. This change means that the second stage of measurements considers only the horizontal direction as opposed to the vertical. Now, as electrons pass through the first apparatus, again, half of them are deflected upwards and half are deflected downwards. Now, let's focus on the particles that were deflected upwards. As they pass through the second stage of measurements, half of them are deflected to the left at 90 degrees and half to the right at 270 degrees. Interestingly, if we focus on those deflected to the left and again pass the stream of electrons through a third stage of measurements, determining either spin up or down 0 and 180 degrees, we'll find that exactly half are deflected upwards and half are deflected downwards. Based on what we've just encountered here, three observations may be made. First of all, if we repeat the same measurements, analogous to asking the same question over and over again, the results will be the same. In other words, definite answers exist. However, there clearly is also some degree of randomness. After all, if we conduct a series of measurements, the final results can indeed vary and appear to be random. Lastly, the mere act of measurement affects the results. Consider what this means. There exists a rather interesting phenomenon you may or may not have heard of. Adult cats have been shown to meow whenever humans are present. That is, in the case of absolutely no human interference. Adult cats will actually have very little reason to meow to one another. Perhaps in the case that they're looking for food, they only look toward a human, at least in the case of a domesticated cat. Now, on a larger scale, similar changes in behavior for animals, even in their natural habitats, just because humans are nearby, have been present across the board. The mere act of observation clearly results in alterations in areas such as research in ecology and biology. At the macro level, staring intensely at a ball won't change its trajectory when the ball is thrown. However, when we consider subatomic particles, which are significantly smaller than the standard rubber dodgeball you might find in gym class, merely shooting photons in the direction of these tiny little particles in order to see them can actually change their state. Consequently, when we consider things on the quantum level, including in the design of quantum computers as well as for generic research, we will need to factor in measurements. For instance, a qubit that is existing in some superposition of several states can undergo, quote, wave function collapse into a single state when observed. This will play a role in how we interpret randomness, qubit-related calculations, and decoherence. Decoherence specifically is a major factor that will be encountered in quantum computers. Keep in mind, quantum computers utilize superposition and entanglement to conduct calculations. This in turn makes the qubits extremely sensitive to the environment. Mere radiation from nearby warm objects or fluctuations in electromagnetic fields can be sources of error. Both fortunately and unfortunately, the Heisenberg uncertainty principle states that the more precisely we measure one particular variable or of a particle, the less we will know about another aspect of the same particle. A commonly referenced relationship is how the more we know about a particle's position, the less we know about its momentum, and vice versa. A rather good analogy written by Aaron McCormick on the Scientific American actually involves the idea behind squeezing a balloon. Consider how squeezing the balloon can actually decrease its volume in one direction, making the cross-section of that balloon skinnier in that region, while also making dimensions of the other parts of the balloon stretched out and bloated. Ideally, we want to be able to squeeze the quantum computing process such that the act of measurement can focus on what we are actually attempting to measure, as opposed to environmental factors. Thus, the act of measurement is something that cannot be overlooked in any respect. Mere observation of the circumstances can alter them, and with quantum computers, any environmental interference can lead to decoherence, decreasing the accuracy of the results. Consequently, a portion of research surrounding quantum computers has been directed towards minimizing decoherence and refining the methods of measurements. So that's all for today. If you have any questions, please do not hesitate to check out the qmunitytech website, as well as just any other resources that are available. Thank you.